All right, we'll continue on talking about mixtures. Just a little review here. So if we have a sample of air, which is 80% by mole nitrogen, 20% by mole oxygen, what can you say about that? Could you say, for example, is this true or false? 80% of the mass of this mixture is nitrogen. True or false? 80% of the mass of this mixture is nitrogen. That would be false, right? Because the molecules of nitrogen weigh different than oxygen. In fact, nitrogen is about 28. No, oxygen is 32. Oxygen is 32, nitrogen is 28. And so they weigh different amounts. How about this? 80% of the molecules in this mixture are nitrogen molecules. Is that true or false? That's true. How about this? The volume of nitrogen is equal to the volume of oxygen. Is that true or false? The volume of nitrogen is equal to the volume of oxygen. True or false? True? True? Anybody say false? It seems like it would be true because this is just one container. And the nitrogen and oxygen are in the same container. So it seems like it's true, but is it always true? No, since it's not always true, we'd probably say false because sometimes it's not true. And so it's true sometimes, so you would be right sometimes, but you would be wrong sometimes, so we can say false. Why? Because it depends on how we look at the mixture, right? How about the pressure? Is the pressure of the nitrogen the same as the pressure of oxygen? So the nitrogen pressure and the oxygen pressure are the same? Sometimes they are, yeah. Sometimes they aren't. It depends on how you look at it, right? And so those are a bit more tricky, but what you have to do is you look at it both ways. You should get comfortable looking at it both ways, in which the pressures are the same or the volumes are the same, right? Where the pressures are different and the volumes are different. You have to do that. Because usually when we have a mole percentage, the mole percentage is the same as the volume percentage, which is the same as the pressure percentage. And so 80% of this by mole is nitrogen. That means 80% of the pressure is nitrogen and 80% of the volume is nitrogen, right? But those both cannot simultaneously be true. And so we have to be careful with that. What else do we want to know about this? You know, the other things we want to know is we got oxygen molecules in here and nitrogen molecules in here. And these are moving in random straight line motion. So we want to know a little bit about the theory, you know, the kinetic molecular theory of this gas mixture. And so what types of things do we want to know? Well, one thing we want to know is the temperature. Is the temperature of the nitrogen the same as the temperature of the oxygen in this mixture? And so the temperature of nitrogen equals the temperature of oxygen. Is that true? No? Not true? Let's say the mixture is at 25 degrees C, like this room. This room is filled with nitrogen and oxygen. And so let's say it's 25 degrees C in this room. So I'm asking you, is the nitrogen in this room at 25 degrees C and the oxygen in this room at 25 degrees C? Do they both have the same temperature? The answer, so if they have the same temperature, that must mean they have the same speed, right? Do they have the same speed? I mean, it's possible one of the nitrogens in here might have the same speed as one of the oxygens in here, you know, but that probability, well, depends on how many molecules there are. But one thing for sure is we think in terms of average speed or in terms of something else. You know, because temperature is proportional to what? Yeah, not just the kinetic energy, because normally when we think about kinetic energy, we associate it with a single particle. We think about it in terms of the average kinetic energy. And so let me ask you this. The average kinetic energy of nitrogen is equal to the average kinetic energy of oxygen. Is that true or false? The average kinetic energy of nitrogen is equal to the average kinetic energy of oxygen. It's true because they're both at the same temperature. The gas mixture, they can't be at different temperatures. And so the average kinetic energy is the same. Since the average kinetic energy is the same, does that mean the speed is the same? The average speed of nitrogen is the same as the average speed of oxygen. No, that's false, right? In fact, we don't look at the average speed, we look at what speed instead? The RMS speed, the root mean square speed. And so the analogy they give in physics is if you have a small car and a large truck, and they both have the same energy, they can't be moving at the same speed, right? The small car must be moving much faster to have the same energy as the large truck in terms of momentum. And so the same thing here, which one's moving faster, the nitrogen or the oxygen? Well, which one's lighter? Which one's the lighter one? Which one's the heavier one? Nitrogen's lighter, so nitrogen must be moving faster. And so nitrogen's RMS speed is going to be greater than oxygen's. But they both have the same energy. Okay, what else do we want to know? Well, the speed, you don't have to memorize the equations because the speed equation, you just have to know how to use it. And so using it's not too difficult. 3RT over the molar mass. Actually, that's not the normal units of molar mass. The molar mass here is in terms of not grams per mole, but kilograms per mole. This is one way. There's another way of calculating URMS, and that comes from the kinetic energy. And so we know that the average kinetic energy is equal to 1/2, this is from Newton's law, the mass of a molecule times URMS squared. So if we solve for URMS is equal to 2e bar k over the mass, and then take the square root. And so there are different ways we can calculate the speed, RMS speed. The kinetic energy is going to do the same. Kinetic energy is going to be based on the temperature, which we saw earlier, which was 3/2 kT. Do you remember that equation? Or 3/2 R over N. What's it? Something like that, right? And so doing these calculations is not that bad. What we want to be able to do is we want to be able to calculate the RMS speed of oxygen, the RMS speed of nitrogen, right? And then compare also the kinetic energies as far as mathematical calculations go. There are two other things that are important in kinetic molecular theory to know, and one of them is something called the mean free path. You know what the mean free path is? Mean free path is how far, on average, a molecule travels before it collides. Let's see. Obviously, the path, you're going to get a distribution, right? Sometimes it travels long distance, sometimes it travels short distance, but you'll get some kind of distribution. And we'll take the average of that. We'll get the mean free. Mean is just the average, another word for average. And so mean free path of gases, think about the air in this room. Air in this room is about 80% nitrogen, 20% oxygen. How far do you think an oxygen travels or nitrogen travels on average before it collides with something in this room? This far, the oxygen molecule is so tiny, but maybe it's here and travels over here and then collides with something, another oxygen. How far? What do you think the distance is? And that's the mean free path. So let's take a look at the mean free path. Of air. And we have a little Wikipedia here. I can show you. And so if we look at the mean free path, well, it depends on the pressure. So we look at ambient pressure. This ambient pressure is 1 atmosphere. 1 atmosphere is 1.01325 bar. Or in terms of millibar, it would be 1,013 millibar. So we have 1 atmosphere pressure, 1,013 millibar. A millibar is close to a millimeter of mercury. You know, 1 atmosphere is 760 millimeters of mercury. 1 atmosphere is 1,013 millibar. So, you know, a little different, but close enough. Okay, so here's the density of molecules in there, and here's the mean free path. And so the mean free path is 68 nanometers. So on average, the molecule travels 68 nanometers before colliding with something. Now 68 nanometers, how big or how long is that? And so nano is what? 10 to the minus 9. So nano is 68 times 10 to the minus 9 meters. That's extremely, can you even see that? You can't, it travels such a short distance, you can't even measure it. You know, even if you put your fingernails together, there's still too big of a gap, right? It seems to be. Because how big is an atom? You know how big atoms are, roughly? The mean free path is about 10 to the minus 9 meters, and the atom is about how many meters? And it turns out, you know, atomic radii, those are around 10 to the minus 10 meters. 10 to the minus 10 meters is a special unit designation in chemistry because atoms are about that size, so we call 10 to the minus 10 meters an angstrom. You know, it's 10 to the minus 10 is not a metric prefix. It's 10 to the minus 10 meters is an angstrom. And so atoms are about an angstrom, or a few angstroms, or 5 angstroms, 6 angstroms in diameter. And so when we're looking at this, well, this is about 680 angstroms. And so 680 angstroms is the mean free path, and the atom is about an angstrom, or a few angstroms, right? And so it does it travel that far? No, it doesn't seem to travel that far. If it only travels 68 nanometers before it collides on average, then there's something else that we should know in order to help us visualize gases. And there's something else we should know in order to visualize gases, which we aren't going to calculate. This is something we can calculate using kinetic molecular theory, but the something else is collision frequency. Frequency there. And so let me right.
Are we saying that the space between those atoms are small, or they just travel at such a fast speed that they collide?
No. Well, the collision, the mean free path is the distance between, you know, molecules before they collide. And so well, let's take a look at the mean free path again. You know, this is an ambient pressure, but what happens when we go to low vacuum? Low vacuum is between 1 and 300. You know, 1 and 300 millibar, or, you know, 1 and a couple of hundred, what we call 1 and a couple of hundred torr, or millimeters of mercury. And so that's low vacuum. Low vacuum is what we can get out of that thing over there, or vacuum pump. But when you go to low vacuum, the mean free path goes from 0.1 to 100 microns. So the mean free path is still way bigger, but 100 microns, is that all that? Can you really see that? You know, is there a ruler that measures to the micron, the nearest micron? No, that's gonna be tough. And so if we go to medium vacuum is usually what a lot of people, you don't really need specialized equipment for medium vacuum. But when you get to high vacuum or ultra high vacuum, then you have implosion hazards and you have leakage and other stuff. So when you're in high or ultra high vacuum, you have to have stuff that looks like a submarine. You know, the walls are extremely thick. you know, all the windows are very thick with heavy-duty gaskets around it. It definitely looks like you're on a ship or in a submarine when you're working with these. And that's because the implosion hazard, it doesn't sound like 14 pounds is very much, but it is. And then the other reason is for vacuum leaks. But when you get to high vacuum, take a look at the mean free path, 1 kilometer. That means if you suck out most of the air, then it is empty space. You know, 1 kilometer of a mean free path it's going to go a long distance before it hits anything. And so you think about the number of molecules if we could get this room under high vacuum, it would be pretty much all empty space. You know, molecules just go and hit that wall and then bounce off and hit this wall or do whatever. And so we're talking very, very long. I mean, in ultra high vacuum, you know, it's 10 to the 5th kilometers. It's huge. And so did I tell you about the experiment they sent out on the space shuttle? Maybe I didn't. Well, you know, generating these kind of vacuums on Earth is so hard because we got 14 pounds of atmosphere pushing down and trying to contaminate everything, right? And so this is very, very expensive to generate, you know, ultra high vacuum. You need all kinds of specialized equipment and heavy duty mechanical pumps. Not only do you have mechanical pumps, you have another kind of pump called a diffusion pump, which uses the velocity of the molecules passing up to suck or, you know, create a vacuum behind it. But anyway, so some guys had a brilliant idea. Why not just attach something on the space shuttle? Because out in space, you know, you don't have this huge blanket of air on top of you, right? It's all pretty much empty space. And the vacuums that they can get out in space are extreme, right? And so they took it out, and then they're trying to grow single crystals on a wafer out in space because they thought, you know, then the risk of contamination is very minimal. You know, risk of contamination here, because there's so many different things in the air, that is very high. So that's why we need these high vacuums to get rid of any potential contaminants might get incorporated in there. And so they took this out in space, but then they brought the, this is a story I heard. They brought the crystals back and analyzed them, and they were much more contaminated than the samples they got on Earth. You know, and they're thinking, why were they so badly contaminated? The reason they were so badly contaminated is, as the space shuttle's flying up there, it's degassing all kinds of stuff, you know, gas molecules, particles, etc., that gets trapped, you know, on the tiles and the exterior surface of this. And so the only way they could really get this is if they left the space shuttle out there for a very, very long time, so it completely degassed. And so there's nothing coming off the surface of it. And so it turned out to be a failed experiment, but an interesting idea for sure. Well, anyway, you can see the mean free paths, but when you think about air, you know, air, that's, you know, under ambient conditions at room temperature and in 1 atmosphere, that air molecule doesn't travel very far before it hits something. And so we have something called the collision frequency. Let me see. There's a collision. I just had a interesting thing. I don't know where I put it. Oh, here it is. This is very cool. I'm going to save this so don't forget it. So let's pick a pressure. So I'm going to pick 760 millimeters of mercury, the pressure we want. And temperature, let's go with 298 Kelvin. And then let's pick an oxygen. Oxygen is probably about 5, this is times 10 to the minus 10 meters. Times 10 to the minus 10 meters is the angstroms, so this would be 5 angstroms, right? Well, let's just guess 5 angstroms, guess. The molecular mass of O2 on average is 32 AMU. Okay, which gives us, let's say, a mean free path of, this is in times 10 to the minus 7, so 10 to the minus 8, 10 to the minus 9. This would be 36 and a half nanometers, or 0.365 times 10 minus 7 meters. That's mean-free path. So the mean-free path is a little longer here, which is about 73 times the molecular diameter. Well, when we're looking at this, the corresponding average molecular speed is 444 meters per second. So that oxygen is moving fast, 1,000 miles an hour. So moving 1,000 miles an hour, it's hitting you, right? So do you feel it? If something hits you at 1,000 miles an hour, you think you'd feel it, but oxygen, a single oxygen molecule doesn't weigh much, right? And so we feel it. Obviously, we feel it, we just don't notice it because we're used to, we're like fish underwater because we're used to, this atmosphere surrounding us. And if this atmosphere wasn't there, then we wouldn't be used to it. Like if you go on a plane, and the cabin loses pressure, then you're in a vacuum, and then you'll notice it. You can't breathe, obviously, but so we notice it when it's not there. We don't notice it when it's there, but anyway, these are colliding with us, generating the pressure. But when we look at the collision frequency, take a look. 1.2 times 10 to the 10th. This is 12 billion collisions per second. 12 billion collisions. That has to be 12 billion collisions per second because how far does it travel before it collides? And so that's 12 billion collisions per second. 12 billion collisions per second, is that infrequent, No, that's pretty, I don't know, if 12 billion collisions per second is infrequent, then I need to change my, my thinking. Because, what did Petrucci say? Let me just check what Petrucci said. Molecules only collide fleetingly with one another and with the walls. And most of the time, the molecules are not colliding. That, I don't really understand what he's saying. Most of the time, the molecules are not colliding 12 billion times in a second, which means that the time between collisions is 10 to the minus 10 seconds. That's like 0.1 nanoseconds between collisions. And so I'm thinking most of the time, so that's why I was saying that's kind of weird, right? In terms of thinking. But you could, oh, here it is, 0.2 to 0.3 nanometers, the average mass, diameters, molecular diameters, 0.2 nanometers. Would be 2 to 3. So maybe I should have put 3 in here. Typical diameter. Let's do that. So even if I use 3 angstroms, which is 0.3 nanometers, it's still, So if we make this one bigger, this one goes smaller. So 22 nanoseconds between collisions, and a collision frequency 4 billion per second. Still enormous, make it a little bit smaller. All right, but the calculation of collision frequency and mean free path, we aren't going to do. The only calculation we're going to do is the speed. We know the molecules are moving fast, right? That's it. All right, let's move on. We'll do an application of this, like Graham's law, later. I'm gonna look at the homework. We're gonna move on from this to another topic, and that is ideal versus real. Let me ask you this. In nature, is there such thing as an ideal gas? No? Is that something that, no, actually there is no such thing as an ideal gas. Why? Well, you know, the ideal gas law is named the ideal gas law because that applies to ideal gases, but if there's no such thing as an ideal gas, then why are we using the ideal gas law? Because an ideal gas, there are two things that make an ideal gas ideal. Do you know what those two things are? I'm sorry? Well, yeah, the pressure is going to be influenced by this, but it's not the pressure. You know, the pressure, there's two things about the gas itself that cause it to be ideal. One has to do with the volume. The volume of the gas particle is 0. The volume of the gas particle has to be 0. Well, here, you know, we assume that this is going to be a volume here because we have some kind of diameter here. So I said that it's going to be about 3 angstroms for the diameter, and therefore you can figure out the volume. But here we're going to say the volume of the gas particle is 0. And we could see this because of Charles' law. Charles' law says that the volume and temperature are proportional, directly proportional. So if the temperature goes down to 0 Kelvin, the volume must go down to 0. And so if you were to cool down a gas, let's say oxygen gas in this room, all the way to 0 Kelvin, does it just disappear into 0? No, that's impossible. There is volume, the particles. And so this is one of the things that make an ideal gas ideal. We treat the gas as having 0 volume. So if I have 1 liter of gas, it's 1 liter of pure empty space. And that 1 liter of pure empty space, the gas particles can go anywhere they want in there.
You're talking about the gas particle itself or the space between?
Not the space between, but the gas particle itself. And so if I have O2 in here, you know, I have an oxygen bounded to an oxygen. And so this particle, which we call the molecule, is going to have a volume. And so the volume of the gas particle is 0.
Because the book was saying something that it had like a little subnote or note at the bottom that said that the volume among the gas molecules, not the molecules, not themselves, not the molecules, molecules themselves.
The volume of the gas?
Between the particles.
The volume in between the particles is the volume of the gas? Where was that? Where did you see that?
Under the Charles' law section.
Charles' law section? Let's go back to Charles' law. Let's take a look. Let me take a look at that. Oh, this footnote here?
Yeah.
All gases condense to liquids or solids before the temperature approaches absolute 0. Okay, this is a different thing. Also, when we speak of the volume of the gas, we mean the free volume among the gas molecules. And so, this is what they mean by that. They mean if I have 1 liter of air, and we consider this 1 liter of empty space. This is ideal. The reality of this is 1 liter of air equals the volume of empty space plus the volume of the particles themselves. Okay, let me give you an analogy to think about. If I have 36 milliliters of water, is that 36 milliliters of water molecule? No. What I have is, if I have 36 milliliters of water here, what I have is 36 milliliters equals the volume of the water molecules plus the volume of empty space between. It's like if you're packing a box of oranges, you have 1 cubic foot box of oranges. Is that, do you have 1 cubic feet of oranges? No. You have the volume of the oranges plus the volume of all the gaps between the oranges. And that's going to give you 1 cubic foot. Now for us, for the ideal gas law, we need this to be all empty space so that the O2 has 1 liter of space to travel in. And so here, what we say is that the volume of the particles is so small, it's negligible, so therefore, the volume of this box is all empty space. But that's not reality, because the reality is the particles themselves will consume some of this. Well, the particles are so small that they don't really consume that much space. And so the real situation is this. When we're talking about a real gas, you know, there is the volume of the particle is not equal to 0, right? The volume of the particle occupies some space. And we have to compensate for that, because if I have 1 liter of gas, you know, I don't have a full 1 liter for that gas particle to move on. And I have to compensate. So that's what they're talking about here. The other thing, the first sentence they're talking about, all gas is condensed to a liquid. And so what happens is, there are 2 things. You know, ideal, this intersects at 0. But the reality is this. The reality is, let's say I have some H2O gas. H2O gas up here, and I want to cool it down. Cool it down. What happens is I can't cool it down very long, because pretty soon I hit 373 Kelvin. At 373 Kelvin, that H2O gas is going to condense into H2O liquid. Well, H2O liquid is going to have a much smaller volume, and it's not going to behave like a gas anymore. And so H2O gas is not very ideal, whereas helium, you know, helium is much more ideal, because helium, you can cool down it'll stay gas almost to 0 Kelvin. Almost to 0 Kelvin. But at 4 Kelvin, boom, it condenses into a liquid. And so it turns out that helium is the most ideal gas, because it stays a gas all the way to 4 Kelvin, but it isn't an ideal gas, because, right, it condenses into a liquid. Well, what causes it to condense? What causes it to condense is, as you slow the molecules down, what happens is, you know, when they're moving 1,000 miles an hour, there isn't much time for the intermolecular forces of traction to take hold. But when you slow down the gas particles, that way they can interact. And if the intermolecular forces of attraction are strong enough, then they stick together. They get stuck, right? But if they're moving very fast, they're just going to bounce off each other. Slow them down, they get stuck, and then more of them get stuck, and pretty soon you have a droplet of liquid, and a condensation occurs. And so the other thing, as far as ideal versus real goes, is in an ideal gas, there can't be any intermolecular forces. So that's number 2. Ideal, we have no IMFs or intermolecular attractions, or repulsions for that matter. So what happens here is, as we cool down the water, if there are no attractions to, coagulate these water molecules, then nothing's going to happen. It will stay ideal. But here, we've slowed down the water molecules enough that they can condense into a droplet, form a liquid. So if there's no such thing as an ideal gas, right, then why are we using the ideal gas law? Because ideal gas law is for ideal gases. And you know what that means is the ideal gas law is always going to give us an error. And so why do we bother using it? Well, the reason we bother using it is because of the magnitude of the error. Sometimes the error that gets introduced by using the ideal gas law is negligible. It's such a tiny error, it's not even going to register. Right? Sometimes the error in using the ideal gas law is significant, and there should be no way we use the ideal gas law for that particular calculation. And so this is the difficulty that you guys have, and the difficulty that you guys have is, when do we resort to other methods other than the ideal? In other words, when is it okay to use the ideal gas law, and when is it not okay to use the ideal gas law? Okay. And so if we do a calculation like this, let's say I have 2 gases. I have oxygen gas and H2O gas. And let's say I have different temperatures. So temperature is 298 Kelvin. Let's say the number of moles is 1. The pressure is 1 atmosphere. And we're calculating the volume. And so the volume is easy. Volume is just equal to nRT over P. Volume here is nRT over P. Just use the ideal gas law, and we get, under these conditions, we get 24.45 liters. 24.45 liters here. Right. And so it seems like a pretty basic calculation. Oxygen gas, water vapor, ideal gas law. Calculate the volume. Well, temperature, pressure, and moles are the same, so we'll get the same volume. But then what we have to do is we have to start thinking, well, it's not just the calculation, because these calculations are simple, just algebra, right? We have to start thinking more. And this is the hard part, because, are these 2 calculations equally as accurate? Looking at the sig figs, well, let's say we use the same instruments to measure everything, and we have the same uncertainty in those measurements. Then do we have the same amount of uncertainty in both these calculations, using the exact same numbers? And the answer is no. And in fact, then the uncertainty in here is much higher or lower than the uncertainty here. This one I would feel is fairly accurate, but this one I don't think is so good. And how did I determine that? Well, how I determined that was by looking at, the 2 factors that cause a gas to either mimic an ideal gas or deviate from ideal behavior. And so let's take a look at those in detail here. What are the 2 factors? Well, one factor is, the effect of the size of the particle. As far as the size of the particle goes, an ideal gas, these green spheres should be 0 volume. And so the more, magenta we see, the better, because that means it's more ideal. And so the smaller the particle, are, the better. And so we want the particle volume to be small, but you know, here the particle volume is quite significant. In fact, when you look at this, the particle volume versus the empty space volume are comparable. And so this would be highly non-ideal, and this would be more ideal, but still this doesn't look so good because particles are still kind of big. And so in terms of size, oxygen versus water, much difference in the size? I wouldn't think there's such a big difference in the size. The other thing that causes deviations from ideal behavior are intermolecular attractions. And so what happens with intermolecular attractions is if this, we're looking at the collision here between this and the wall. If we have three other molecules that are attracted to this, then there's another force of attraction pulling it back. Therefore, if it's being pulled in different directions here, then it's not going to strike the wall with as much force as it would if there were no attractions here. And so basically intermolecular attractions will cause it to deviate from ideal behavior. And the two effects we think in terms of pressure. What do you think intermolecular forces of attraction will do to the pressure of the gas? Well, compared to ideal, the pressure of the gas should decrease. And so intermolecular forces of attraction cause the pressure to deviate. In other words, the pressure is going to be smaller if we factor in intermolecular forces of attraction. Okay, the finite, if the volume is smaller, if there isn't as much free space in here, then the bigger these particles become, or the less empty space there is here, that's going to cause the pressure to actually go up, because if you have 1 liter of empty space, then you're going to have some mean free path, you're going to have some collision frequency. But if you have less than 1 liter now, because the particles are occupying some of that 1 liter, then you don't have as much space, and the collision frequency is going to go up, and the mean free path goes down, and the pressure goes up. Pressure is going to go up. And so on the one hand, these have opposing errors. One causes the pressure to go up, the other causes the pressure to go down. So maybe they cancel each other out. And they do to some extent, but let's take a look at the behavior here. And so the way we're going to consider the behavior of these is by looking at this ratio, which is PV over nRT. PV divided by nRT should give us 1. And so we expect that for an ideal gas because PV equals nRT. This ratio is called the compressibility factor. And we can take a look at the compressibility factor as a function of pressure here, as total pressure. And so if we look at the compressibility factor, we see that some of these, well, one is ideal, so the dashed line here is ideal behavior, but some of these drop down, this one goes up, and so what we see is we see deviations from this. Now, in terms of the compressibility factor, it's PV over nRT, so just look at the pressure. If we keep the volume fixed, the moles fixed, and the temperature fixed, and just allow the pressure to vary, we see the pressure drop. What causes pressure to drop from ideal? Intermolecular attractions. Intermolecular attraction. And so when we look at this, CO2 has stronger intermolecular attractions with one another than O2. Hydrogen, are the intermolecular attractions between hydrogen molecules very strong? No, and so we don't see much of a drop. In fact, we don't see any drop there. And so the pressure drops here, and then it goes up. Well, it's going to go up because as the total pressure increases, the volume gets smaller and things get more compressed, and There's less room, and so the pressure is going to increase due to the volumes. We see that those two factors cancel one another out here for oxygen and here for CO2. And so one makes the pressure goes down, the other makes the pressure goes up, and they effectively cancel each other out, and we get the correct answer using. But this is just, by coincidence. By coincidence, the two are equal and opposite. And this would be like a broken clock. A broken clock is going to be right at least once a day. Well, the same thing here. And so looking at the compressibility factor, we can see deviations, and we can see significant deviations from ideal behavior. So when do we have to worry about using the ideal gas law? Well, let's take a look here. And we can see. Gases tend to behave ideally at high temperatures and low pressures. So high temperatures and low pressures, we expect gases to behave ideally. High temperatures, because the molecules are moving so fast, intermolecular forces of attraction aren't so significant. And low pressure, because at low pressure, you have very long mean-free paths, right? At low pressure. And so it's mostly empty space. But gases tend to deviate or behave non-ideally at low temperatures. Low temperatures because the molecules can attract each other more significantly. And at high pressures means things get crowded, and the volume of the particles themselves are going to be significant. And so what we need to have is some kind of cutoff temperature. At this temperature and above, it's ideal. At this temperature and below, it's not ideal. But the problem is we don't have a temperature like that. For example, for water, 373 is considered a low temperature, because at 373, gaseous water should condense into a liquid. And so for water, we want temperatures much higher than 373 to keep behaving like a gas. Really ideal. But 373 Kelvin for helium is an incredibly high temperature, because helium doesn't condense until we get all the way down to 4 Kelvin. And so even 100 Kelvin would be considered a high temperature for helium, even though 100 Kelvin for liquid water, that'd be a solid block of ice by then, right? And so high temperature, is very difficult. We don't have a single number because it depends on the gas, how strong the intermolecular attractions are in that gas. For helium, no problem, room temperature. For gaseous water, room temperature, probably a problem. What about pressures? 1 atmosphere. Is 1 atmosphere high pressure or low pressure? And so pressures are a little easier to deal with if we look at the compressibility chart. When we look at the compressibility chart, we'll see this. These pressures are enormous, 200 atmospheres, 400 atmospheres, all the way to 1,000 atmospheres. How often are you doing something at 1,000 atmospheres pressure? It's enormous pressure. And so you can see right at the very beginning is where gases are going to behave ideally, because they all start at about 1 here, right? And so that means at extremely low pressures, extremely low pressures would be maybe up to 5 atmospheres. Up to 5 atmospheres, we barely left the beginning, the origin here, right? And so maybe from 0 to 5 atmospheres, no problem. We're okay. But once we get to 10 atmospheres, we're starting to deviate, right? Much more for CO2 than for H2 and O2. At 100 atmospheres, we're way out. And so it depends. At 1 atmosphere, no problem for the gases we're dealing with. But when we start going 10, 100, 200 atmospheres, then is the ideal gas law going to work? No, not at all. And so we have to use some judgment as to okay, so let's say, let's do an example here. The examples would be things like this. Well, we have some gases here. And actually, let's take a look at these numbers in a moment. But what we can do is we can model this behavior here using mathematics. And if we model this kind of behavior, then what we do is we just try to figure out how to fit this with a mathematical equation. In other words, we're just taking our raw observations, these measurements, and fitting them to a mathematical equation. If we were to fit these to a mathematical equation, then we call that equation an empirical equation or a law. And so here, this is what was done. There are a number of people who did this. One of them was van der Waal. There are others. Virial did it, and a number of other people came up with different empirical equations. And so this would be the van der Waals equation or the van der Waals law, you could say. Van der Waal was very interested in intermolecular forces. But anyway, what he did was he just took the ideal gas law and put a couple of corrections, mathematical corrections in here that fit the data. Well, it depends on the gas. So one of these is a pressure correction. And so if you look at the variables here, we have A, N squared. Well, N is the number of moles, V is the volume. And so this is the kind of the density of molecules, you know, how many molecules you have in some volume, squared. So it has strange units. But it's going to show that square dependence. And then A, well, the bigger the A, the bigger this term becomes. And so as A increases, what has to happen to the pressure? Well, as this term grows bigger, then this term has to grow smaller in order to equal nRT. And so as A gets bigger, the pressure has to decrease. Well, what causes the pressure to go down in a real gas? Intermolecular forces or volume of the particles? Intermolecular forces. And so let's go back and take a look at our chart here. Where did that chart go? I guess the chart came before van der Waals equation. Okay, in an ideal gas, A is going to equal 0 because there are no attractions in an ideal gas. And so looking at all these gases, which of these gases is the most ideal? Which is going to have the weakest intermolecular attractions? Helium. Helium is going to be the most ideal, with the weakest. That's why you have to cool helium all the way down to 4 Kelvin. That's almost 0 Kelvin in order to get the intermolecular forces of attraction strong enough to coalesce them into little droplets. So it liquefies at 4 Kelvin. And so an A value of 0.0346 is very weak. Hydrogen is pretty ideal also. You know, hydrogen has extremely weak intermolecular forces. Which of these gases has the strongest intermolecular force of attraction? You'd think maybe something like ammonia. Ammonia has hydrogen bonding interactions. Hydrogen bonds are very strong intermolecular forces, but when you look at it, it's 4.2. They're stronger. SF6 is stronger, but this is the strongest of them on the list. And that would be, what's the name of this? Propane. If you look at propane, why is propane so strong? Because does propane have hydrogen bonding interactions? No. Propane only has non-polar, weak dispersion forces. And so if those dispersion forces are so weak, then why is this number so big? And that's because dispersion forces can be very strong. In fact, dispersion forces can easily be stronger than hydrogen bonding interactions. in fact, ammonia is a gas. Propane's a gas also, but it's easy to liquefy propane. When you go buy propane, you usually fill up a tank, and inside that tank is liquid propane. It's just compressed propane. And so here, yeah, it's bigger. But why is it bigger? It's bigger because, you know, of the scale, how this scales. You know, if we made this molecule bigger, like 3 nitrogens with a lot of hydrogen bonding interactions, then it would be stronger. But based on sheer size, this is a small molecule, this is a much bigger molecule. As these hydrocarbons get bigger and bigger, the strength of the attractions grows. So not only can you have a gas that's easily liquefied, you can have a liquid. So when we get to hexane, hexane's a liquid. When we get to something like 15 carbons, 20 carbons, that's a solid. The intermolecular attractions are so strong, it fixes the molecules in place in a solid. And then we have things like asphalt. You know, asphalt, how strong? Do you see the asphalt molecules vaporize into the air? Asphalt's made out of hydrocarbons like this, but they're extremely long chain hydrocarbons. And those don't vaporize all the time. You don't smell them all the time, except when it's hot. And so these can be quite strong. But anyway, here we have from the least ideal propane to the most ideal helium. The factors influencing. Okay, the other deviation from ideal behavior is the volume. Because when we normally put the volume of the gas, PV equals nRT, the volume is the volume of empty space that gas molecule is free to roam around in. But we know that if I had 1 liter of gas, that 1 liter is not all 1 liter of empty space. That 1 liter, some of that volume is going to be taken up by the volume of the gas particles themselves. And so what this does is this. Okay, as the volume of the particles grows bigger, right, this term grows smaller, and therefore the pressure term has to grow bigger. And so we see the 2 factors. 1, the intermolecular forces of attraction will decrease pressure. 2, the volume of the particles themselves will increase the pressure. Yeah. Okay, so let's take a look at our table here. And so an ideal gas is thought to have 0 volume. That's what makes it ideal. And so the most ideal gas on this list is one with the smallest volume term, volume correction, which is B. The volume is going to be liters of particle volume per mole. And so the one that has the smallest is obviously helium. So helium is as close to ideal as you're going to get for gas off the periodic table. And so here, helium, and the worst is going to be propane, because propane is the biggest of these molecules here. And so let's do a comparison here. In this example, we want to compare, I must be missing something. We want to compare this, the volume of oxygen versus the volume of propane, CH3, CH2, CH3, under the same conditions. And so the conditions here, we're going to take 1 mole of gas, right? We'll do 1 atmosphere at 298 Kelvin. So here, the volume of oxygen, when we use the ideal gas law, it should be 24.45 liters. Volume of propane using the ideal gas law comes out to 24.45 liters. Now, is oxygen an ideal gas? No, there is no such thing. So what we think of is, you know, how much does oxygen deviate from ideal behavior? And so you think, well, first thing, at 298 Kelvin, is this a high temperature for oxygen or a low temperature for oxygen? High temperature or low temperature? It's a high temperature because oxygen liquefies maybe around 70 in the 70s or the 90 Kelvin range. And so you would have to cool down oxygen to extremely cold temperatures to get it to liquefy. And so it'd be pretty high temperature. How about propane? Is 298 Kelvin a high temperature or a low temperature for propane? When you go fill up a tank of propane, or when you go buy a tank of propane from like Home Depot or someplace like that, it's liquid inside there. You know, you grab it and you feel it slush around, right? And so is 298 Kelvin a fairly high temperature or somewhat low temperature? It'd be a low temperature for propane. And then you think in terms of volume. You know, the volume of O2 is fairly small because O2 molecules are tiny, but propane molecules, a lot bigger. And so this one is going to be fairly accurate, I would suspect, because, you know, O2 under these conditions is pretty ideal. You know, most gases under ambient conditions behave ideally. However, this is fairly ideal. However, propane, I would expect larger deviations, right? And so here there's going to be uncertainty in this calculation. And so this calculation I probably trust. This calculation, I don't know if I should trust it or not. Well, how do you know if you should trust that calculation or not? What we should do is we should do a comparison calculation. You know, for example, we should calculate the volume using the ideal gas law and then compare it to the volume that we get using the van der Waals equation, because the van der Waals, all it did was fit experimental data using these fudge factors here. You know, these values just come from fitting the mathematical lines here. And so let's do that, and that way I can get a better feel for these. It turns out that calculating the volume is pretty tough. So I'm starting off with a tough calculation. A much easier calculation is calculating pressure. If I calculate pressure, you know, just rearranging the van der Waals equation, the pressure is equal to nRT divided by V minus mV minus A n squared over V squared. And so this is not bad. You just plug in the variables. You know, you have to do a little bit more math. It doesn't take that long. If I want to calculate the volume, on the other hand, I need to solve this equation for V. How would I solve this equation for V? Now looking at this is V to the minus 2, this is V to the positive 1. What should I do? Well, I got to multiply both sides by V squared and get it in the numerator. So multiply both sides by V squared, and pretty soon I have well, V squared times V is V cubed. So pretty soon I have a cubic equation, which is AB cubed plus BV squared plus CV plus D is equal to 0, you know, cubic equation. Are cubic equations easy to solve? Or no, cubic equation, how many cubic equations have you solved? I don't know, a few, maybe graphing it, or you know, maybe using a programmable calculator. But officially we aren't allowed a programmable calculator. Officially we have to solve this using our standard scientific calculator. And so this is the one I want to start off with. I want to start off with kind of a challenging problem. And this is the reason why we use the ideal gas law, because, you know, using the ideal gas law, as long as the gas is close to, or reasonably close to behaving ideally, boy, this calculation is so easy. You know, the volume is just equal to nRT over P, and we don't have to worry, you know. Any gas, you know, we treat these two the same. If they're both behaving ideally, then they should both behave similarly to this. But when we go to the real gases, then we have to look, you know, what is A, B for O2, what is A, B for propane, and plug those in. And so, how would we do this using van der Waals? Good question. Well, one, we hope we don't have to use van der Waals. For O2, I probably wouldn't bother doing van der Waals calculation. For propane, I might think about doing it. But let's do the calculation and see, okay? how big of a difference it is. And so the volume of CH3, CH2, CH3 using the van der Waals is equal to what? And so this is complicated because it's a cubic equation. So what should we do? Well, what's often done in science is we don't solve it exactly. We solve it approximately. Complicated, difficult to solve. And so equations of this sort, we have a technique that we use, and in Chem 1B you're going to use this more frequently than Chem 1A. But the technique that we use to solve these is an approximation method. It's called method of successive approximations. Method of successive approximations. And so let me give you a little different example here. This example, let's say I had purchased 1 pound of propane. Propane's easy to measure the weight of, because once you get it as a liquid, then you just weigh the tank before and weigh the tank after. You can figure out how many pounds of propane you have. 1 pound of propane is not that much. You probably get a lot more, like 10 pounds of propane. But we'll just do it for 1 pound of propane. 1 pound of propane, we're going to, this is propane liquid. We're going to let the propane liquid vaporize into the gaseous state, and we're going to figure out, you know, for this 1 pound of propane in the gaseous state, under a temperature of 298 Kelvin and a pressure of 1 atmosphere, what is the volume? Okay, and so here, first we'll do it ideal. You know, ideal, we need to know the number of moles. And so the number of moles of propane is, we have 1 pound, we'll just say exactly 1 pound, that way we can ignore sig figs. The 1 pound of propane, we have, is it 2.20 pounds per kilogram. So this will give us kilograms of propane. And then we'll go to grams, you know, 1,000 grams per kilogram. Okay, then we'll use the molar mass of propane. Propane has 3 carbons. That would be 3 times 1201. Gives us 3603. And 8 hydrogens. Hydrogen's 101. Gives us 808. This is 4411. And so we have 4411 grams of propane per mole. Propane. So that should give us how many moles of propane we have. And so we'll plug this in down here into this. V equals nRT over P. We got N. R is 0.08206, T 298, P is 1 atmosphere. And so what is the volume come out to? Well, actually, how many moles of propane did you guys calculate? Ten moles. Okay, give me more digits. 10.3048. Okay, 10 moles of gas. Each mole of gas is 24.45 liters under these conditions, about 25. So we got about 250 liters, roughly. But let's go ahead and calculate because we want a little more accurate number. So we'll plug this in here. And that gives us a volume of what? Does someone have it? $10.3048 times 0.08206 times 298. Three things. 251.992 liters. I'm ignoring sig figs here. I'll just say exactly 1 pound. And ignore. I'm only allowed 3 sig figs. About 252 liters. But you know, the temperature's marginal because you know it's easy to liquefy propane at room temperature, right? Add a little bit of pressure. And the temperature is an issue, and also the volume of the particle might be an issue too. Although 1 atmosphere, probably not too bad, but still the volume of propane is kind of big. And so let's compare this number to the volume we calculate using Van der Waals. So using Van der Waals equation, we should get a more accurate answer because Van der Waals is going to correct for those deviations. The problem is how do we solve this equation for V? Well, we aren't going to solve this equation for V. Let me give you a simple example of the method of successive approximations. The method of successive approximations is also called the guess and check method. For the guess and check method, we don't really solve it. We don't really have to solve it. So for example, this, you could solve it. X is equal to 6 divided by 3, which is equal to 3. Guess and check is you just guess an X value. What X value do you want to guess? 2. Plug it in and see, does 6 match with 6? Right? That's the guess and check. So we look at the left side compared to the right side of the equation. We don't set it equal to 0. That would be a mistake in the guess and check method. And so we just leave this equation like this. Here's the left side of the equation, here's the right side of the equation. Let's get the two sides to match by guessing different numbers. And so if we look at it, it's P plus AN squared over V squared. You know, V minus NV. You don't have to memorize this equation. Is equal to nRT. Now, we go back and look at A for propane. And the A value for propane is 9.39. The units are in bars, liter square per mole square. And so the pressure needs to be in bars here. And so we'll just make a note of that. The pressure has to be in bars. R has to be in bars to get it to work. Okay, so well, let's first do that. The pressure is, actually, this is what I made a mistake on, maybe in the morning class. What is 1 atmosphere in bars? This is very close. It's 1.01325 bars. 1 atmosphere is equal to that. You don't have to memorize this number, it will be given. N, what did I say, 1 mole? V, that's our unknown. A, let's figure out what A is. So going to propane, A is 939. And the units will work out. So I'm going to ignore the units because it should work out. The V is going to be in liters, right? So that's what we're solving for. N is 1 mole. Now B is in liters per mole, so that's liters of particle volume per mole. And so if I have a mole of propane molecules, the propane molecules themselves will occupy about 90 milliliters, 90.5 milliliters, or 0.0905 liters. And so this is going to be 0.0905. N is 1 R. Now, I can't use the 0.08206. Why? Because then the pressures won't cancel out. And so I have to convert this to bars. Do you know how to convert atmospheres to bars? To convert atmospheres to bars, we would multiply this by the conversion factor. That is, there's 1.01325 bars per atmosphere. And that would convert our gas constant into bars, liters bars per mole Kelvin. And then T is just 298 Kelvin. And so what we do here is we get this ready to punch in our calculator so we can do calculations quickly. And that is, this is going to be 1.01325 plus, what is 1 squared? 1 squared is 1, so this is just going to be plus 9.39 over V squared times V minus N. N is 1, so it's just B minus 0.0905 is equal to, can somebody punch this out? 0.08206 times 1.01325 times 298. What does that come out to on the right side? Zero point zero 83. Actually, it's got to be bigger. I think it's got to be bigger than that. Can you recheck it?
24.777. The times 298.
Yeah, did you do the times 298? Sorry.
24.7.
Yeah. What did you get? 24.7778. We have too many digits there, but we want a lot of digits there. And so we'll call this the left side. What we want to do is we want the left side to match the right side in this. And so what we're going to do is we're going to guess a V value, plug that V value in here, and then see how close it comes to our target. Our target is 24.7778. All right, so let's go ahead and guess a V value. Does anybody want to guess a V value? So we guess a V value, and then we'll calculate the left side and see how well it matches with the right side. The right side is fixed, 24.7778. Let's see. And so guess a V value that's going to give us a left side that's close to 24.7778. Does somebody have a good starting guess? Maybe 5 liters? 1,000 liters? What volume should we use? What volume will solve this equation? Well, you know, the best guess is, what was the volume we calculated from the ideal gas law? 252? Is that it? From previous calculation. And so the best starting point is just use one that should be fairly close. I mean, it depends on how much this deviates from ideal behavior, right? But we'll just assume it's ideal and it should give us a volume of 252 liters. We don't want to put too many digits in here because that means the calculation is going to get more complex, at least for our first guess. And so what we'll do is we'll just plug it in here. Here. And so this is 1.01325 plus 9.39 divided by v squared. So this is 252 squared equals times v minus, well, 252 minus this, you know, and see what that comes out to. So can somebody calculate that? All right, sometimes what you want to do is you want to use a spreadsheet because spreadsheets help doing repetitive calculation. So what I did was I just typed in the formula for this up here. I'll show you here. The formula. I think this is right. Can you check the formula? So I got 1.01325 plus 9.39 divided by v squared. V squared is in cell A3 here. A3 squared times v minus nb, so that would be A3 minus 0.0905. Does that look right? So I do that and then let's do this. So at 255, you look at the left side of this, does it match the right side? That's way off. So I thought I must have done an error in the formula, maybe.
side, didn't we have like 10 moles or converted it to 1?
Oh, right. That's my error. It's not 1. My error was I was doing 2 different calculations at the same time. And one with 1 mole of gas, the other with 10 moles of gas. And so it was way far off. Unfortunately, we don't have enough time, but let me show you. We have to do n squared minus nb. Ah, thank you. And so n squared, I need to add that in here. And so what was that? It was 10 times 10 point, what was it? 3048 squared. And then here, this is minus n, which would be 10.3048 times that. $261. Okay, I gotta fix my formula here. I'll do it later, but we're out of time today. We'll do it next time.
The program is plugging in, is it plugging into 255 liters? Or is it plugging into 25
255. 255 because that was our calculation base. The volume should be 255, so we're guessing the volume is close to 255. And so that's why I'm plugging it in here at 255. And it should work. Well, there's other checks. We'll look at this next time to figure out what happened.
How you got a cube and a square on the other side?
Oh, it's not cube. It's a cell A3.
Oh, okay.
It's cell A3 squared, what it should be.
Okay.
So when's the last day of turning this? Or get a check. When are we going to get a check?
Experiment 18, last day to get a check will be Thursday. Yeah,
Okay.
17 is kind of already passed.
Oh, okay, okay. Wait, were we supposed to turn it in?
No, not yet.
And also,